Hello, and I'm going to have a look at a ballistics pendulum problem here. However, I've decided to make it a little bit more entertaining. Instead of a bullet and a pendulum, we're dealing with Tarzan and Jane. So here's the situation we have right now. We've got Tarzan, who's running away from some forest animal, probably a jaguar or something like that, and he's got a mass of 90 kilograms, as can be seen right here. Now, Jane is standing perilously at the edge of a cliff, and her mass is 65 kilograms. Now, she already has a vine and is quite ready to swing. So, what this means is, once Tarzan grabs her, the two of them will go swinging out over the cliff and will find safety. However, in the water, as we can see in this wonderful picture that's been drawn here, there is a crocodile that can jump out of the water. This crocodile can jump a total of 3 meters above the cliff face. So what I'm curious about is, how fast does Tarzan have to run in order for him and Jane to swing to safety? Well, the first thing that I would do with this is I would have a look, I would work almost backwards. I know how high they have to swing, so I would take a look at the energy situation of the moment right after Tarzan grabs Jane and starts swinging. So right at that moment, we know that we can take a look at the energy. So we know our equation for energy is the kinetic energy initial plus the potential energy initial plus the work external is going to equal the kinetic energy final plus the potential energy final. Great. Well, let's just have a look at these for a second. Initially, they're both at the same ground level, so my potential energy is 0. Also, because we're dealing with a pendulum, we know that the work external is going to be 0 as well. This leaves just the kinetic energy beforehand, which is great. It means that we can know the kinetic energy of Tarzan and Jane the moment after Tarzan grabs Jane. Now afterwards, we know that they're going to swing up to that 3-meter mark there. Now that means that when they reach that peak point there, Tarzan and Jane's velocity is going to be reduced to 0. But their height is going to be at that 3 meters. So I know that kinetic energy is going to become 0. So this is great because it allows us to have this equation simplify for us down to kinetic energy initial equals our potential energy final. Now, having a look at our equations here, I know that the equation for kinetic energy is going to be 1/2 mv squared. And my equation for potential energy is mgh. Now, given that we're looking at this situation right now, the moment after Tarzan grabs Jane, I know that the mass is actually going to be mass of Tarzan and Jane for both situations there. However, looking at that, I can see that I've got the mass of Tarzan and Jane combined on both sides. So what this means is I can simplify this equation even further, which I always love to do, because simplifying things makes the equation that much nicer for us to look at. So now I'm left with 1/2 v squared equals gh. Now the only thing I don't know here is the initial or the velocity when right after Tarzan grabs Jane. So I will solve for that. Multiplying both sides by 2, I end up with the velocity squared equals gh times 2, which I know is 9.8 times 3 times 2. Plugging this into my handy-dandy calculator, I can see that 9.8 times 3 times 2 equals 58.8. So the velocity squared is 58.8. Now, that's great, but I don't want to have that velocity squared. I'd like to find just that velocity. So I'm going to take the square root of both sides. That's going to cancel out my square there. I'm going to be left with just the square root of 58 equals the velocity. So my velocity becomes, plugging it into our calculator here, second function square root 7.668 meters per second. So that's great. Now we've got the velocity that Tarzan has the moment after he grabs Jane. So the trick with this is that's kind of like uh, a before and after, and now we want to look at the before and the really before. We want to look at the moment before Tarzan grabs Jane and the moment right after he grabs Jane. So let's have a look at that. So just kind of having a look here, my before is going to look something like this. I've got, as it was up there, I've got Tarzan running with some velocity uh, towards Jane, who's holding a cord. And then my afterwards is Tarzan and Jane both swinging to safety. So, with this, I can solve this by just remembering about conservation of momentum. So conservation of momentum says that if I find the momentum of Tarzan, the momentum of Jane, and I put those two together, it's going to equal the final momentum over here of Tarzan and Jane together. So let's just see if we can figure this out. Well, we know that momentum equals mass times velocity. Well, Tarzan is traveling at some velocity. We're not certain what that is. But mass of Tarzan times his velocity of Tarzan. That's going to be added to the momentum of Jane. But now, how fast is Jane traveling? Well, Jane is standing still right now. She's waiting for Tarzan to come save her. So her velocity is 0. Since her velocity is 0, I know the momentum of Jane is going to be 0. But now, the moment afterwards, I can see finding their momentum just the same way. However, here, I know that their total mass is going to be the mass of Tarzan plus the mass of Jane, because they're holding onto each other, they're holding onto that vine, they're swinging, they're trying to escape the crocodile. Great. So that's their mass, and that's going to be times their velocity. And now their velocity is the one that I just found up there, which means the only velocity that I don't know in this situation, the only variable I don't know in this situation, is Tarzan's velocity. So let's put this together and see what we can come out to. So my momentum before is Tarzan's mass times Tarzan's velocity. And that's going to equal the mass of Tarzan plus the mass of Jane times their velocity. So dividing both sides by the mass of Tarzan so that I can get my velocity by itself. That cancels with that. And that leaves me with the velocity of Tarzan equaling all of this stuff on the right. So just plugging in what we know, I know that the mass of Tarzan is 90 kilograms. The mass of Jane was 65 kilograms. Their velocity, we found, was 7.668. And that's all divided by Tarzan's mass of 90 kilograms. So plugging this in to our handy-dandy calculator, what do we find? That times, so 7.668 times 90 plus 65 gives me a nice large number, but then I'm dividing that by 90 as well. This gives me a total velocity for Tarzan of 13.2 meters per second. Now, that's great, and that's the solution we were looking for. That was Tarzan's velocity. However, a really neat thing that I love to do is I love to figure out what this means in kilometers per hour, because that's something that we're all a bit more familiar with, and it never hurts to brush up on conversions. So, Tarzan's traveling at 13.2 meters per second. I want to change that into kilometers per hour. So, I want meters on the bottom, kilometers on the top. I know that's 1 kilometer for 1,000 meters. And then I also know that I want hours on the bottom and seconds on the top, and that's a conversion of 3,600. Whoop, had that the wrong way. So it's 3,600 seconds for 1 hour. Here our hours are going to, hours are going to remain, but our seconds are going to cancel with that, our meters are going to cancel with that, and I am left with Tarzan's velocity in kilometers per hour. So let's see, we've got 13.2 times 3,600 divided by 1,000. Tarzan is traveling at 47.5 kilometers an hour. So he is traveling really fast, significantly faster than I can run. So I hope this has helped you figure out some ballistic pendulum problems, and have a great day, morning or afternoon, whatever it happens to be.